n squared algorithm to approximate alpha from Amdahl's law. It has to be a nearly linear. It has to be a linear algorithm, basically, or nearly linear, like n log n. So quicksort is the right thing to choose there to approximate alpha. So there were actually two problems. One was the one that Ben mentioned about the merge sort. That's actually not as bad as the using an order n squared sort at the bottom level for the sort. So the merge, the tree-based merge, is actually proportional to n, and so that's okay in terms of approximating alpha. But using the order n squared sort, don't do that. So if you want to get a good grip on how your algorithm was doing with alpha, use quicksort. Don't use bubble sort. Yes.
Were the alphas at all consistent?
The alphas, for people that use quicksort, I was getting alphas between around 0.7, and they were generally consistent. And then there were people that were doing bubble sort, and they were getting alphas bigger than 1, because the cost of the sort was just reducing dramatically with problem size. And if you look at Amdahl's law, it's talking about essentially you need linear growth to do Amdahl's law. And there are more sophisticated, Gustafson's law is the one that you would use in this particular case, but there's not like a clean way of writing out Gustafson's law because it depends on that growth of the bottom level algorithm, whatever you happen to do. So again, it was an idea that I thought of in the morning and talked about in the afternoon. There's the dangers of doing that. And you're going to see the same thing with the game theory. It's just not my thing, so I haven't spent much time thinking about it, so you'll just have to bear with me. That said, I plan to redo the stone tree today in a way that actually makes sense. And then we'll talk about we're going to talk about implementations of the game tree part of tic-tac-toe. That said, I'm about halfway through doing my own implementation, so it might be that on Wednesday I have some great insights about different ways of doing things. But we'll talk about it today, and we'll just see how far we get. Luke, you had a question about putting sketches on the web. What's the question?
I was just wondering if you could review exactly how that works.
Okay, so let me just get rid of my public HTML. So you're logged into your MATLAB account. The first thing you need is a place to put your HTML files for the server. The server is told to look in a particular location in everybody's home directory, and that location is public underscore HTML, all lowercase, and that is an underscore there. So now I've created this folder. The next step is to put something in the folder. To put your sketch in the folder. There are a number of ways to transfer files from your computer to the MATLAB. I'll illustrate one using FileZilla, which is a free file transfer piece of software that runs in Mac and Windows and whatever else. The first thing you want to do is go up and pick a host name. It can be any of the lab machines that are running SSH servers, so it's the 6 in the back of the room, or you can just use math. It doesn't really matter. And maybe, yeah, okay. Yes, you have to create that folder with the make directory command that I just.
In this primary.
You could do it on in this application as well, but yeah. If you're using FileZilla, make sure you do port 22. That's where our SSH server is. That's where most SSH servers are. And hit enter, and you'll see some progress stuff at the top while it's thinking. And you'll know you're successful when your MATLAB directory appears in the right-hand window. There's the public HTML file or folder. And as Josh just kind of indicated, I could actually, I think, just right-click here and create a directory and call it, junk. And I could do all of this stuff from within FileZilla. What I need to do now is browse around for a directory, a sketch over on my files. So my files appear on the left-hand side. Just for the sake of organization, I think it's best if you put your sketch inside a folder that's inside public HTML, right? Because if you put more than one sketch on there, which you will, they're going to have to be in different folders anyway, at least the way that I'm showing you how to do it. So here's a sketch folder right here. Some stuff that I was doing, I guess, in class on Friday in 167. So I can just drag that whole folder over to the public HTML directory and wait a second, and then it'll appear. So it's copying as we speak. So now it's there. If I go back here, I see that folder is now there. I literally just created that folder using the file transfer software. Let me switch into that folder, and there it is. I don't even know if this is a functioning sketch, but we'll just see what happens. The next thing to do is to get a template index.html file that I've placed on the web, and so you can use this exact same command. So wget http yada yada yada. Remember, this is case sensitive, so it's capital P processing, and then index.html. If I hit enter, it's going to go ask the server for that file. The file is going to be transferred and placed into the current directory. So index.html wasn't there, and now it is. And the last step is to open up your index.html and tell it about this file right here. So I'm going to highlight the name of this file so that I don't have to memorize it. I'm going to edit my index.html with Vim or whatever your favorite editor is. And down here at the bottom, instead of referring to example.pde, we want to refer to the sketch that we just put in there. And that is essentially the bare minimum. That's all you really have to do to get your sketch working. Let's go to...
Were you recording?
Yes.
Okay.
Well, okay, there's that, and there's also, you know, I don't put this stuff up here for no reason. There's also this sketch, which is this link, which is exactly the same as what I'm doing right now. Okay. All right, so go to math.whitman.edu. This has to be math.whitman.edu, unlike the file transfer thing. The web server is only on math. I think it's APR_26_2013, maybe _bubbles. And again, I don't even know if this works. It does work. Okay. So when I type in this URL, which is, you'll notice you don't see the word public HTML here, right? All I see is ~shulaw, which is my user ID in the math lab, and ~shulaw is aliased to this public HTML directory. And then other things that are inside that directory you can list in the URL. So in this case, April 26, 2013 bubbles. And when I list that, what happens is the web server goes to that directory and it'll try to list the contents of the directory unless there's an index.html file in there. And if there is an index.html file in there, it will render that file. So if I go up a level, since there's no index.html file in that folder, it just shows me what's in the folder. And that's the default behavior, but if there is an index.html file, then it'll render it. Is that enough for everybody?
Last time you showed us this not on the web, I'm pretty sure the bubbles didn't bounce off the top.
Well, that's just because maybe that was the April 23rd version or something, or April 22nd version. I've been working my way through different topics and processing in the intro class. And so this is just a further iteration of the same sketch. In this sketch, they get stuck on the bottom, and if they sit there too long, they turn red and die. I think they also, yeah, and there's a bounce cost. So when they hit the top, they bounce back like 75% of the way. So it's a slightly inelastic bounce. Yeah.
Will Is the sketch only that box? Like, does it know that that's as big as the canvas is and that's fine?
It does. So
like for tic-tac-toe, we don't have to worry about things getting wonky when we upload it?
right.
Okay.
So it's going to key off of that size command.
Right.
One word of warning, or however you want to take it. You're developing in processing, and then you're taking the PDE file and you're moving it over to a web page, right? Processing is built out of Java. And when you take the PDE file and move it over to the web server, what you're doing is taking that program and running it in JavaScript. And the reason that it works is some really brilliant people at Processing.js wrote a little processing library. See this thing right here, processing-1.4.1.min.js? That is a simulation of the processing environment that is written in JavaScript. The simulation is about 95% faithful, but the devil is in the details. That 5% that they haven't managed to simulate can cause problems. If you just keep it simple and just use some of the things that I've been talking about in class, you're not going to run into any of those weird compatibilities. But if you launch out on your own and start using, some really sophisticated, for example, processing, when you're working in the little processing editor, everything that you can do in Java is available to you in processing. Everything. But if you go down that road and you start getting into some really quirky bits of Java, when you take your thing over to JavaScript, it's going to fail, because this is not a 100% faithful emulation of Java. It's 100% faithful emulation, or 95% faithful emulation of processing. So keep that in mind. Right. So if you want to not worry about that, processing very easily exports to Java applet, and then it's 100% no problem. But I'm not a big fan of Java because it requires the user to go out and get this third-party plugin, whereas JavaScript is built into all these browsers. And ultimately, from a computer science perspective, they're both Turing-complete languages, right? So whatever you can do in one, you can do in the other. It just might be a little bit harder. So I just tend to, when I'm writing in processing, I just tend to keep it simple and not go after the really fancy stuff that's in Java.
Really quick question, just to review. When we're getting the index.html file, does that go in, or so it goes in the public HTML?
And inside the folder that you put your sketch in. So I'm encouraging you to not only have a folder for your web directory, your web stuff, but then to actually put the sketch in a subdirectory of that folder. And then the index goes in there. Because you can have an index in every one of your folders that'll behave the same way. Any other questions about this stuff? Yeah, what was that one that just kicked our ass last summer? That one incompatibility. Does that ring a bell? Like we went from processing and we put it on the web. Was it like a null pointer? I don't remember. Or no, it was a typing issue. Like it was.
I ran into one with a float cast int.
Maybe that's exactly what it was. Yeah, it was a float cast to int. And it was doing like float division, and I wanted it to do integer division or something like that. Yeah, JavaScript assumed it was a float, even though my processing sketch explicitly declared it as an int. When it landed over in JavaScript on the web, JavaScript, which is a weakly typed language, just let it be a float. And suddenly I'm doing float division instead of integer division, and it was kicking my ass. Took a long time to figure that one out. I don't know if that was you and I, Evan, or if that was just something I was doing on my own, but yeah, that was a tough one. Okay, let's talk a little bit more about the game stuff. I'm going to pull up David's book here and just show you where I'm getting my information. Yeah, here we go. Okay, so we started talking about this stone game where you pick up 4, 3, or 2, or whatever, 1, 2, or 3 stones. And you play this game, and the last person to pick up a stone is the loser of this game. And I started marking up this tree, forgetting that I wanted to do max and mins, not just maximums. So what I want to do is mark up this tree again, and we can have a more reasonable discussion about this particular game. So I'm going to go through, and everywhere there's a 0B, that's a win for B. Everywhere there's a 0A, that's a win for A. And I'm going to call a win for A +1 and a win for B -1. And then what I'm going to do is min-max my way all the way up to the top. So let me do that. So every A node is going to be the maximum of its children, and every B node is going to be the minimum of its children. And don't let me forget that as I work my way up. So we'll go through, and there we go. So every B node every 0B is a win for B. So let me go through and do the B's. And I'm just labeling the leaves. These are the only ones that have sort of independent value. I don't think I missed any. And then let's go through and do the A's. Did I get all the leaves? Okay, so working my way up. So for interior nodes, if you're an A node, you're going to take the maximum of your children. So in this case, you're -1. I'm just going to go black now, here and here. So the maximum of its children is -1. And then working my way up, B is the minimum of its children, also -1. Here's a B node, so I want the minimum of its children, that's +1. And here's an A node, so I want the maximum of its children, that's a +1. Let's keep going. Here's a B node, there's only one child, so it's got to be +1. Here's an A node, I want the maximum of its children, so that's a +1. Here's an A node, I want the maximum of its children, that's a -1. Here's a B node, I want the minimum of its children, that's a -1. Let me prop up my... So I've got this first leftmost subtree going at the first level. Moving up, that's a +1. Let's see, that's a +1. That's a -1. B is a -1. That's a -1. That's a -1. And then A is the maximum of its children, so it's -1. So that's a loser for A, right? And then let's talk about Yona's question of adding in that extra possible move, which would be a 1B. And then that would lead to a 0A, right? So 0A, we decided was +1. And then B takes the minimum, but there's only one child, so that's also a +1. And then A takes the maximum, and that suddenly becomes a +1, and now A has a winning strategy. Okay? Okay. So, let's go back to David's notes here, and we'll just look at some of the technical stuff here. So, the only way that we can do what I just did is if I can get down to the leaves. So you can see that this is a problem for writing a chess program, because you don't get to the leaves in a chess program, not generally speaking anyway. And it's a problem for most interesting games. You don't get to the leaves. So the question becomes, okay, that's an interesting algorithm for the stupid stone game, and it kind of works okay for tic-tac-toe because the tree is still small enough to handle. But is this a useful algorithm for other games where we don't get to see the leaves? And the answer is kind of, yeah. It all boils down to, and I'll let you read through this, but it boils down to this function, this E function. So focus on this bit here. So in general, we want to talk about a function that places values on the nodes. That function is a lot harder to do when you're not talking about the stone game or the tic-tac-toe game. What you do in chess is you build the tree out maybe 5 deep, right? So you look at all the possible moves out 5 deep. And then what do you have? You have these kind of incomplete games, right? Partially played games. And what the electronic chess researchers try to do is place values on those incomplete games. Does it advantage black? Does it advantage white? And all of the work in that exercise is evaluating these incomplete games and trying to decide which one is more valuable to white, which one is more valuable to black, and which one is, sort of neutrally valuable. And unlike the stone game, where every value is either plus or minus 1, for chess and for more complicated games, these value functions, v of x here, these value functions take a range of values, depending on how good the board is for black or how good the board is for white. But they're imperfect. Right? You could have a board that looks really terrible for white, and then white could win out of that board because you don't get to go all the way to the end and see. So it's as much an art as it is a science when you're building chess playing programs. But there are kind of sub-results that you can get, like rating these incomplete boards. There are very sophisticated, very mathematical approaches to rating these game boards, even though you don't get to see the leaves. So it's not like black hat, just look at it and guess. There's definitely a systematic way of evaluating these incomplete boards. Have you heard of Deep Blue, the chess playing program? I think that's the one that beat Kasparov the first time. IBM made it. And I think the last time, so Kasparov played that, I don't remember when that match was, it was in the 90s sometime, and Kasparov played that a 5-game match, and I think he won 1 of them, and then lost 3 in a row or something like that, or maybe lost 2 in a row. I don't remember what the order was. He actually did win 1, and that's the last time that anybody beat Big Blue, or it might be called Blue Gene now, I can't remember. And so we passed a moment in time there, at least with respect to chess, when the computers permanently became better than the humans. It's unlikely that a human is ever going to go back and do better than the computer moving forward. So those researchers that build those chess-playing computers spend a lot of time on these value functions. Yes?
So then, like a default application on the Mac is you have a chess program that you can go ahead and do a little slider, right? Make it more or less difficult. Is that just the amount of time it spends thinking about what the optimal move will be?
There are a lot of different things that slider does, but the most common one is how far it looks ahead.
Okay.
So I think Deep Blue or Blue Gene at the time Kasparov was playing was looking ahead 18 moves. which is staggering.
Okay.
And that slider just knocks it back to 2 moves or 1 move or something like that, because then the valuations get necessarily weaker. Yeah.
And those trees take into account every possible move.
Well, they don't, right? So if you're really trying to go down 18 moves, what you have to do is learn to prune off sure losers, right? And you can identify sure losers, or losers that are like 99% sure losers.
So like, don't move your queen into an area guarded by a pawn.
Bingo, right, exactly. And so there's just as much optimization as you could possibly imagine when they're building these chess playing programs, right? You do as much as you can. The more optimization you can do, the deeper you can go into the tree. And the deeper you can go into the tree, the better chance, right? When you get within 18 moves of the end, in some sense, whatever that means, right? Because chess is an indefinite game. But when you get within 18 moves of the end, if there's a winning strategy, Deep Blue's going to find it. And you're not. So that's an interesting. It's an interesting thing to think about. If you want to read more about this, there's. I looked up a couple of things. I was curious about checkers. I didn't know what the status of checkers was. It is solved, but it was fairly recently. It was 2007, which I did not know. So I just typed in checkers game.
So mean there's a winning strategy, or does it mean that we can build a whole game tree?
So for checkers, they check the whole game tree, and I think it ends in a draw for perfectly played. But there are these 3 definitions up here that you can read. I'll just let you read them while I read them.
Imagine trying to do a game tree for Go.
Yeah, Go is definitely.
It's one of the hardest games to make a tree for. Like they have like rankings of how good like human players are at the game, and it's like just like half of what the highest level is.
It's funny that you mentioned that, because I've never played Go, and having read about game theory for the last few days, now I want to start playing Go.
Go is so complicated.
Because it's complicated and yet it's simple.
Yeah, the rules
right?
are
The
simple.
rules are so simple, and yet the best Go players crush the best computer players. So, and people are working hard on it. Go, the best Go players in Asia are like rock stars here. It's a really well-respected game. So you have these 3 definitions of weak, ultra weak, weak, and strong. Strong is the one that we've been talking about, where essentially you kind of, essentially you can see the whole game tree. And then there's a summary down here. So drafts is is checkers, and yeah, according to this anyway, it was in 2007 that it was weakly solved. So it hasn't been strongly solved, but you can always play it to a draw, essentially. Largest game that's been solved to date. It took 18 years to do the calculation and 200 computers. Some of these I've never heard of. A lot of these I've never heard of. I've heard of Hex. I've never played it. And then there's some information down here. Oh, and tic-tac-toe, trivially solvable. And then there's a little bit about chess.
I love the last humans usually done a 19 by 19 board, which is 145, whereas maybe more complex.
And then there's the comment about Go.
Wait, 5-1 in games. Oh, so stick beats.
And Reversi is an interesting game. I didn't realize that it was still. I mean, I guess it makes sense. It's a large game board, 8 by 8. So it seems to still be fairly mysterious. I don't know what else is down here. Yeah, okay. But yeah, I want to play Go. If anybody wants to play Go, let me know. Okay, let's talk a little bit about how your game is going to use this game tree. So let's pretend that I write an AI to play this game. What's the AI going to do? Let's say the AI plays first. So what's the AI going to do?
Is this the altered game or the original one?
Let's play the original one. Exactly, right? There's no obvious choice here. They're all equally bad. And so it'll just randomly pick one. So let's pretend that it goes down here. So then what do? You're B.
Take 3 pieces.
Take 3 pieces. I go down here and follow the minimum child. Yeah.
How does a tree like this, is the problem with the tree like this just that it's so simple that like one side is never going to make a mistake? Because this doesn't take into account, like, if I was playing against another person and had this information, I would always go for either 3 and probably 4 because there's more opportunity for them to mess up. So do trees like this take into account, I mean, obviously this one doesn't, but would a more complicated tree take into account the least bad, like the less risky?
So if you want to go that route, right? So you know you're in a losing position right at the get-go. So you want to go down the most complicated side of the tree. The problem is the way that this goes, at least with this valuation system, there's no rating about the depth of the tree on that side. But you could certainly throw the depth in at every node and just choose based on that, right? Choose the one, all things being equal, choose the one that's deepest, because then you have the best chance of getting your opponent to screw up. That's absolutely a reasonable thing to do, and it probably does happen in some AIs.
The value based on your depth.
Say again?
You can just call it leaf that's supported -4.
Yeah, so you could actually put that in the valuation function itself. So you get the idea. Let's think about what this looks like in tic-tac-toe. So tic-tac-toe starts with X. Oh, that was a bad choice. There. It starts with an X. And I guess we can just call it, maybe we'll call it 9X or something like that. What does it look like below this node? Yeah, there are 9 possibilities. Okay, and we'll go in any one of those directions. And what does that look like, right? Well, it's, systematically it's maybe like that. And then maybe like that. And you get the idea. You just work your way across. You put an X in every possibility. So each one of these nodes has a partially played game in it with 1 X. Now these are all O moves, right? These are all 8 O's. What does it look like below one of these nodes? There are 8 places to put the O. So this game tree, it's not like every node has the same number of children, right? The deeper you go in the tree, the fewer children there are. Okay. Now, what I'm asking you to do, and I've actually already put the homework assignment up there, is I'm asking you to analyze this tree to pick the best move. So you're going to go down to the leaves. So let's go way down here. And you get down to a leaf. What does a leaf look like? This is Yeah, this is a finished game.
Yeah, but it's not necessarily for that.
Oh, okay, valid point. Like, that one would never happen. Because you would have already won before you
Yeah.
placed.
Right.
Yeah, no, it's
So yeah, you're checking for wins as you go, essentially. Okay. So there's going to be some recursiveness going on in your implementation, and then one of the stopping criteria for your recursive algorithm is, well, if you get to a leaf. Well, what is a leaf? A leaf is either a winning game board for X or O, or a full game board, and the full game board could be a win for X, a win for O, or a draw, right?
So basically, you just check win first. No, you want to check full first, and then win or loss, because then you get.
I think it could be also a draw.
Draw.
Yeah.
Okay.
Yeah, but you check for wins.
So it won't be a win for O. You're right.
Yeah.
Sorry,
You could
I
check for
interrupted.
wins first, because then your draw thing doesn't actually have
Yeah.
to check.
So in your recursive algorithm, you're going to be checking for that kind of stuff. Essentially, you're trying to find leaves, right? And a leaf is a finished game, whether that's a win or a draw.
So recursive algorithm just mean a tree traversal?
Yeah, we're going to be doing tree traversals, and we're going to be doing them in post order. So what does post order mean? Do you remember?
Right.
Left, right.
And this is not a binary tree, so more generally, what does post order mean?
All children.
Children and then root. And that makes sense, right? If you look at this thing up here, I can't place a value on this node until what? Until I've placed values on all the children.
And we're already assuming that any unnecessary nodes have been eliminated.
For at least the way that the assignment is written right now, I'm not asking you to be smart at all. So, what I'm going to ask you to do is start and place a value on every node, every child at the first level. So that's going to mean going down here and doing all the stuff down here and then placing a value. And it's going to be +1, 0, or -1, right? And then I'm going to move to the next one, do all that stuff down here, whatever it is, and get a +1, a 0, or a -1. Right? What do those three values represent? Win, loss, draw. Win for X, draw, win for O. So I'm not going to ask you to be smart about it, and it's not really important at this particular stage of the game because the tree is small enough. You could literally generate the whole stupid tree and store it in memory and search it later if you wanted. We're not going to be that wasteful. But I am going to be wasteful enough to just ask you to determine the values of all the children at a particular level. So you're doing the first move. You're up here. You're 9x. You get the values of all the children using some recursive algorithm that goes all the way down, like for this guy, it goes all the way down to the leaves. Gives values to all the leaves, and then works its way up using the min-max algorithm. And it's going to get all the way back up here, and it's going to put a value in that node. Then you're going to go and turn your recursive algorithm loose on the next node, and it's going to put a value on that node. All the way across, you're going to have plus, minus 1, or 0 all the way across. What's 9x's move?
Which is
Doesn't matter. Pick a +1.
yeah.
Pick a +1. And if you want to add some extra valuation on there, like the deepest side or something, and hope that the human makes a mistake, that's fine. But I'm not asking for that at the moment, mostly because I haven't written the implementation myself yet, and so I'm a little uncomfortable about asking for too much when I haven't done the program yet. Yes.
In our last program with Marshall, you gave us the sort of a clever algorithm for implementing a binary tree using arrays where like the children are. Is there a way to cleverly implement?
Absolutely. I mean, you can just assume that every node here has 9 children and just not use some of the children.
Yep, there you go.
Okay, but it's extraordinarily wasteful.
Yeah.
So what I'm going to at least ask you to do, because I know that this actually works, because like I said, I'm about halfway through my implementation. I'm sitting here at node 9x. I want to write an algorithm, a recursive algorithm that'll put a value on this node, and then call it on this node, call it on this node. And if any of these nodes is null, meaning there's nothing down there, right? Then it's not going to put any value on it at all. Okay? Because there's not anything there, right? Because I want an algorithm that generalizes to deeper levels, right? Because deeper levels don't have 9 children. They have 8 or 7 or 6 children. And so the algorithm that I write is going to ignore missing children. That's what we want to do. So I'm going to write an algorithm, and I'm going to just call it on this node and get a value, and then call it on this node and get a value, and call it on all the nodes all the way across. And I'm going to do that, so then I'm going to pick a move. So I'll have this guy. And when I get in there, now I've got 8 children that I need to look at. So I still have 9 children in my tree node. I have 9 child pointers. I just ignore the null one and do the rest of them. And I assign values to those 8 nodes, and I pick the minimum. And then when I go there, I assign values to the 7 nodes, and I pick the maximum. And I go to the next one, and so on and so forth. Yeah.
Are you using an array list with this then?
Okay. I actually built a tree node. So let me show you a little bit about that. So class T node, and inside, let's see, I have a weight, and then I have an array of tree nodes. Okay, and in my constructor,
The syntax for making a class and processing.
I'm following it right now.
Okay.
Yeah. So I'll talk about the arguments in a minute, but inside the tree node, I'll just set the weight to something that's safe, that indicates meaninglessness. Right? I don't want to like initialize the weight to 0, for instance, right? Because that means something in this situation. So I'll just, it's easy to pick an out of range weight. So you know, W equals -5 or something like that, right? There are no -5 weights in the game. So -5 will be a signal that this is a meaningless weight. And then in here for I equal 0, I less than 9, I plus plus, I'm just going to set all of these. Oh, sorry, one more thing. And I'm going to do a child equals new T node 9. So now I've got an array of T node pointers of size 9. So the class data here, there's a weight which I'm going to need in order to figure out which move to pick. And then there's this list of child pointers. And let's just keep going. And then I want to initialize, I want to make sure that I initialize all of these guys to null. And I don't know if Java recognizes both upper and lowercase null, but I know lowercase null works. So at this point, you've got a list of T node pointers, but they're not null. They're just junk. And so then I have this for loop to make sure that they're all null, because my recursive function is going to rely on that null to make sure that it doesn't, to recognize an empty tree. I think that's the extent of it, and I might have thrown in a weight. I can't remember if I decided to throw in a weight init.
So if you were being like really pedantic about a number, you could have an argument that would have size the based on what level
The number of children, yeah, exactly. And then down here you write your recursive function, like your weight function, int w. And in fact, let me show you Gishard's notes, because he actually implements. So there's a bit of trickery to help you with the min-max stuff, but and you can read about it. But here's a post traversal. And let's see how this works. Here's a tree node, and the goal is to put a weight on this tree node. So what's the weight of this interior node? If it's a leaf, in tic-tac-toe, it's going to be 1, 0, or -1, right? So we want that to happen if it's a leaf. And otherwise, we need to look at the children and do a minimax thing. And this guy actually does that. It's not quite everything that you need for tic-tac-toe, but it's not bad. Let's think about what's going on here. If the left child is null, so what is he talking about here? Well, the kind of node that David has in his head is a little more sophisticated than the node that I just wrote in my notes. David's node has a weight in it, and it has a linked list. And a linked list, right, that's probably the right thing to do, because a linked list isn't a fixed length. You can just add as many children onto the linked list as you need. So if you were working in a more general game where the number of possible moves was 11, and then you could use the same node, because a linked list can grow as large or as small as it needs to be. So in David's linked list, the left child is essentially the first thing in the linked list. L child is the first thing in the linked list. And he's looking at this thing and saying, if the left child of X is null, what does that mean? There are no children, which means that this is a leaf node. So just return the value of the leaf node. And we've got this function e prime, and that prime is not proper C syntax. He's just pulling it in from his notes. Earlier he talks about a function called e prime right here. So be careful when you read that. That prime is not some weird C syntax. If the left child is not null, then there's at least one child. So now what happens? You start working your way through the linked list. So L child is kind of like the head of the list. It returns the head. And we get Q is now the first child. Okay, what are we going to do with that? We're going to evaluate. We're going to put a weight on Q. That's a recursive function call right there. And when we're done, we're going to have the weight of Q. And then we're going to go through sort of a cursor implementation of the linked list. We're going to traverse the linked list. rsib, what do you think that means? rsib Q. That advances you through the linked list to the next sibling. While the next sibling is not null, advance the cursor. Q is equal to rsib Q, the right sibling, and call the maximum of temp, which is the first value, and the subsequent values. When you're done, the final value of temp is the maximum of the child weights, right? And then you return it. And like I said, that's 90% of what you need to do. It's just, for us, for our purposes, it's just tweaking what does it mean in the context of tic-tac-toe, and are there sort of easier ways to do it.
Can I ask just why is there a negative?
So why is there a negative? He discusses this, but maybe you can figure it out. It alternates. It's really clever, because remember that when you're going through the max-min thing, if it's B move, you're looking for the minimum, and if it's A move, you're looking for the maximum. you can actually accomplish that by introducing a minus sign on the weight function. And when you call minus w, and then inside that it calls minus w, and inside that it calls minus w, it's flip-flopping all the way down. It's an alternating sequence.
It's so clever.
It is. It's terribly clever. And you read about it, and it's funny because as over the weekend when I was writing my own implementation, I hadn't really read this stuff, and I was like, how do I flip this thing back and forth? Oh, I could just put a minus sign in the argument. So I didn't do it exactly like that, but it really does. If you start working in it, it just naturally, it's the way to do it. Because that way you can take max all the time. Yeah. So it's really clever. And you call this guy, you set this guy loose on each of your children. You're trying to pick a move. So what do? You set it loose on each of the children, and that return value goes into each of the children. And then how do you decide which one to do? If you're A, you take the max, and if you're B, you take the min. Okay, we're out of time. I'm sorry, 5 minutes over, but we'll talk more about this next time. And we'll just keep it simple and see how far we get.
Are there any